On the evening of June 24, 1982, British Airways Flight 9 was cruising smoothly at 37,000 feet above the Indian Ocean, bound for Perth, Australia. The flight deck was calm, the weather radar displayed a completely clear path ahead, and the crew was managing what appeared to be a textbook transoceanic crossing. But in the pitch-black sky just south of Java, an invisible hazard was drifting quietly into their flight path. Hours earlier, Mount Galunggung, an active stratovolcano, had erupted with immense force, sending a massive plume of pulverized rock and ash high into the upper atmosphere. Unlike standard storm clouds, which are packed with liquid water droplets that reflect radio waves back to an aircraft's weather radar, volcanic ash contains virtually no water. To the radar screen glowing in the cockpit, the deadly ash cloud was completely invisible. As the airliner entered the invisible plume, the flight crew noticed a mesmerizing, unnerving phenomenon. Bright trails of electrical static, St. Elmo's fire, began dancing across the cockpit windshield, glowing with an intense, unnatural clarity. Within moments, a faint sulphurous haze began wafting through the passenger cabin, accompanied by what smelled like burning electrical insulation. What the crew couldn't see in the darkness was that their massive four-engine jet was plowing through a dense cloud of microscopic glass, silica, and pulverized granite at over 500 miles per hour. Every second, millions of microscopic rock particles were relentlessly sandblasting the airframe, stripping the paint off the leading edges of the wings, and gradually grinding the thick outer layers of the cockpit windshield until they became completely opaque. While the airframe suffered physical erosion on the outside, a far more dangerous thermal process was unfolding deep within the jet engines. Modern airliner engines rely on extreme heat and precise airflow to generate thrust. Air is compressed, mixed with atomized jet fuel, and ignited inside the combustion chamber, where temperatures routinely exceed 1400 degrees Celsius. Volcanic ash, however, is not soft timber dust or organic smoke. It consists of microscopic fragments of glass and volcanic rock with a melting point of roughly 1100 degrees Celsius, well below the operating temperatures inside the combustion chamber. As the engines ingested thousands of cubic feet of ash-laden air every minute, the microscopic rock particles instantly liquefied into a sticky, molten glass slurry. This molten glass washed directly over the high-pressure turbine blades, coating the delicate cooling passages and aerodynamic vanes in a thick, liquid glaze. As the air moved past the combustion zone toward the turbine section, it cooled slightly, causing the molten glass to rapidly solidify into an impenetrable, ceramic-like enamel. The precise aerodynamic contours of the engine components were destroyed, suffocating the delicate balance of pressure and airflow required to keep the engine running. Deprived of oxygen and choked by hardened glass, the engines began to surge, shake violently, and flame out. Within 90 seconds of entering the plume, all four engines on British Airways Flight 9 fell silent, transforming a 100-ton airliner into a massive, unpowered glider at 37,000 feet. Faced with total engine failure over water at night, the crew executed their emergency checklists with textbook composure. Establishing a clean glide pitch, they turned the aircraft back toward the coast of Java, calculating that their remaining altitude gave them roughly 20 minutes before they would be forced to ditch in the ocean. The descent brought an unexpected salvation. as the unpowered jet glided down through 13,000 feet into denser, cooler and cleaner air. The severe thermal shock caused the brittle glass glaze baked inside the turbine assemblies to crack and shatter. Small pieces of hardened enamel broke free and blew out through the exhaust nozzles, gradually clearing the choked air passages inside the engines. Working methodically against the ticking clock, the flight crew attempted engine restarts, successfully relighting all 4 engines one by one as they cleared the bottom of the ash layer. Though one engine surged again and was shut down for safety, the crew brought the remaining 3 engines up to landing power. They faced one final hurdle. The sand-blasting effect of the ash cloud had turned the front windshield completely opaque, leaving only 2 small strips of clear glass at the extreme side windows. Relying heavily on instrument displays and peerless crew coordination, Captain Eric Moody brought the plane down safely onto the runway at Jakarta, landing blind without a single injury among the passengers or crew. The incredible survival of Flight 9 redefined how global aviation treats volcanic hazards. Nearly 3 decades later, in April 2010, the world witnessed the full economic and operational weight of those lessons when the Icelandic volcano Eyjafjallajökull erupted. The eruption ejected a massive plume of fine volcanic ash directly into the high-altitude jet streams that sweep across Western Europe. Grounding aircraft was no longer an overreaction. It was a non-negotiable safety mandate. Aviation authorities closed European airspace for 6 straight days, canceling over 100,000 flights and stranded millions of travelers worldwide, prioritizing structural integrity and engine safety over commercial pressure. Today, the global aviation industry leaves nothing to chance when a volcano awakens. 9 specialized Volcanic Ash Advisory Centers, known as VAACs, monitor the planet 24 hours a day using real-time satellite imagery, seismic sensor arrays, and advanced wind dispersion modeling. The moment an eruption reaches high altitude, these centers issue immediate, mandatory navigational alerts, drawing precise 3-dimensional exclusion zones through the sky. Modern airlines will routinely spend tens of thousands of dollars in additional fuel to divert an aircraft hundreds of miles around a volcanic plume. They know that behind the quiet beauty of an eruption lies the one substance a jet engine can never digest: microscopic glass that can freeze the skies in a matter of seconds.